I'm Nathaniel, and today we are now going to do question 2 of STEP 2020. And just a little update here, I have been interviewed by the NUS on my mathematical abilities, and so shout out to Prof. Goh Se Song for giving me this piece of feedback that I should be speaking slower, which I am doing right now, and providing more steps. So that's exactly what I am going to do now. So you can see here, the curves C1 and C2 both satisfy the differential equation. Now, as you can see, this is very obviously a differential equation question. And now here comes the fun part, where k is the natural logarithm of 2. Now, I personally have this strange attraction to the natural logarithm of 2 because what drew me to it was this: 1 minus half plus 1 over 3 minus 1 over 4 plus ... And this is called the alternating harmonic series. And then, while doing a Maclaurin series on the natural logarithm of 2, I have obtained this other series which I have never encountered before, and I thought this was one of the most miraculous series to ever exist because the terms grew at an exponential rate. And both series, as obviously, can be divided into Maclaurin series of ln 1 plus x at 1 and negative half. Had enough of fun facts already? Good. So, let's suppose that dy over dx is kxy minus y over x minus kxy. So what do? We cross multiply, meaning that we multiply both sides by x minus kxy. Dy over dx equals to kxy minus y. Now what we do is that we factorize both sides. The one on the left, the terms have a common factor of x. So we have x, 1 minus ky, dy over dx. Now on the right side, the terms have a common factor of y, and then we get y, kx minus 1. So what do? Well, one can use an integrating factor, but this doesn't seem like the right format. So one thing we are now going to do is that we're going to divide both sides by xy. Why? Let's see, x over xy equals to 1 over y, and there's only a y on this left hand side. And similarly, y over xy equals to 1 over x, and there's 1 over x coincides perfectly with this x. So this is to ensure that we can perform separation of variables. And if you haven't heard of it, it's where we put all the x's on one side, usually on the other side, and then the y's on the dy over dx side. So we have done the separation. Now we're going to integrate both sides. But wait, have we simplified them yet? So we will continue our workings and see. 1 over y minus k, since y over y is 1, dy over dx equals to k minus 1 over x. Because if we times kx times 1 over x, we get k, because the x over x cancels out. Now, we are going to integrate both sides. 1 over y minus k dy equals to k minus 1 over x dx. And then, this is what we get. Ln mod y minus ky equals to kx minus ln mod x plus c. Well, this is what we have right now. And what do we do about it? Do we mitigate the c first? No, we don't. Instead, we put the natural logarithms on one side. Why? It is because we are going to take the exponential of both sides later. So this means ln mod y plus ln mod x equals to kx plus ky plus c. Then using the addition rule for logarithms, we have ln mod xy, because ln a plus ln b is ln ab, you know the drill. And then we factorize by taking the common factor of k away into another bracket. So we're now going to exponential of both sides. And then we put a here, because you know the exponential of x a plus b equals to x a x b. And then you will have ab log ac equals to c to the power of b. Then we have a times e to the power of kx plus y. And since k is ln 2 and e to the power of ln 2 equals to 2, we would have xy equals to a times 2k to the 2 to the power of x plus y. That's it. Now, we're going to derive a similar result for C1 and C2. We're going to split up our working into two parts. So C1, C2. 1 times 1. C1 passes through the point 1, 1 as stated in the question. So we will have 1 times 1 equals to a times 2 squared. 1 equals to a times 4. A equals to 1 over 4. Xy equals to 1/4 times 2x plus y. That's it. Now, do you want to multiply both sides by all? Sure you do, because it's all the part of mathematical simplification. 4xy equals to x. 4xy is power of 2x plus y. That's it. Now, we are going to use what is called the quarter square formula. For 4xy, it's dead simple. Just take x plus y squared minus x minus y squared. And it turns out, and you really do expand both sides, it turns out that you actually get 4xy. Understand? Great. This is our equation for C1. Now, it's a bit long-winded, but trust me, you get it. So, we multiply C2 passes through -1, as stated in the question. -1 times -1 equals to a times 2, -2. A equals to 4 because 2 to the power -2 is a quarter. Then this means xy equals to 4 times 2x plus y. Now we're going to take 4xy equals to 16 times 2 to the power x plus y. Now you might think this is making the problem a lot harder, but then you realize that the last side could be written as 2 to the power x plus y plus 4, and then the left side could be written as the same. So this we have C1, and then we have C2. X plus y squared minus x minus y squared equals to 2 to the power x plus y plus 4. Now, we are just going to scrap everything for now and just put the equations of C1 and C2 somewhere else. Now, why? So, this will take a while. So, we have our two equations. X plus y squared minus x minus y squared equals to 2 to the power x plus y squared plus x minus y squared minus is 2x plus y plus 4. I'm sorry, this might be a little illegible since I'm writing on a pad instead of writing on a piece of paper. Now, hence show that y equals to x is a line of symmetry for each curve. For x plus y, it is dead simple. Just use the commutative law. Hence, this and this would be the same. But what about this bit? X minus y squared equals to x squared minus 2xy plus y squared. And then using commutative law, we have y squared minus 2xy plus x squared. And then, wait a minute, it's y minus x squared. So therefore, x minus y squared is invariant to transposing the variables over x and y. There, we have proved it. Sketch on the same axis the curves y equals to x squared and y is 2 to the power of x. Now, we are now going to sketch it on the graphic calculator. No, it's not going to be fun at all. Besides, we're not going to improve on our graph sketching abilities. Instead, we're just going to do it by hand. And you know the x squared, it's a parabolic shape curving upwards. It's like this. And x 2 to the power of x is actually an exponential curve cutting the y-axis at 1. So we are now going to plot some axes here. 1. And then you see here, then x squared being here. Hold on. This may take a while. So then is this sliver here where, sorry, it's taking a lot over. So we are now going to find the intersection points of each curve. Turns out that x equals to 2, y equals to 4, x equals to 4, y equals to 16. You might have heard of this and you just mucked around in your calculator sometime, which I personally have. Now, Hence, show that C1 lies between the lines x plus y equals to 2 and x plus y equals to 4. Now we are assuming that, now, since x minus y squared equals to 2x plus y, wait. That's it. This is our curve x1, but we have our equation rearranged a bit. Since x minus y squared is greater than or equal to 0, x plus y squared minus 2 to the power of x plus y must be greater than or equal to 0. Now, we are going to scroll down a bit so that we can do the rest of the working. So, you see, now we add 2 to the power x plus y to both sides. X plus y squared must be greater than or equal to 2 to the power x plus y. So, we are going to substitute z for x plus y. So, z squared must be greater than 2 to the power of z. Now, we obviously know this can't be true if z goes to infinity, because 2 to the power of z is obviously a faster growing function according to ON notation. That's Landau's big O. So, then this should be at where 2 less than or equal to z less than or equal to 4. Why? Turns out that we have 4, then we have z equals to 3, then we have 9, 16, then this is our x squared, and 2 to the power x would be 4, 8, 16. If you try it out for like 2.5 and 3.5, you get that fact that z squared must be greater than 2 to the power of z. Now, we have successfully proved that C1 is finite. However, C2 does not have such limits. So, as you can see here, if we do the same thing, but instead we have 2x plus y plus 4, and z squared must be greater than 2 to the power of z plus 4. Now, you see, 2 to the power of z plus 4 is just 2 to the power of z, but just shifted 4 units to the left. And it might not have the same intersection points, but there is definitely one where z must be less than 0. Therefore, C2 has no bounds at all. Now let's just hop into Desmos to sketch curves C1 and C2. So as it turns out, I plugged into Desmos and we have the two equations here. Now the reason why I didn't decide to do these by hand is because it would be too tedious and inaccurate. So we're gonna hire a machine to do it for us. Fortunately, Desmos is free and I encourage all of you to use this. And besides, it's also a cool vector graphics design program. Change my mind if there's anything better out there. Now, let's see. We have C1 here. There's this bit where the x plus y equals to 2 and x plus y equals to 4. But also there's this infinite bit here. Why? It's because if we saw x squared and 2 to the power of x before, there is an intersection point around here. So therefore, this definitely means that x plus y equals to this unknown value. It should go less than that because x squared is greater than 2 to the power of x. Now, C2 is a bit simpler because we only have one intersection point at, let's get this right, -2. And since we got this, and there will be no finite bit here because there is no such value in there. There's no such value where x squared is greater than 2 to the power x plus y plus 4 and x is plus y is greater than 0. Now, do you understand how to do curve sketching right now? So, as a math student, and possibly all math teachers might tell you, you might need to have some number sense. As in, like, you can estimate your answer to within an order of magnitude. That's called Fermi estimation. However, I encourage you all to have a kind of graph sense. Like, you see, if you have the intersections, you can just predict where the x plus y lines would be and where the curve would lie. And so it will have it will be helpful for you to estimate your graph along the way, not just mechanically calculate values, because we all know this is impossible for implicit functions like this. Alright, well, see you in another step video. Thank you all for watching.